why the 2.5D is kind of okay these days? Any idea? But when you move to this kind of true 3D, you face a lot of this heat dissipation problem. Why is that?
The logic chip is where all the heat, most of the heat is dissipated.
The amount of toggling in a logic, like in a processor, would be more than that would be in a memory.
Yes,
so
exactly.
Memory less than a processor.
So you can do the DRAM stacking without too much problem because the DRAM is memory, and when you access memory, the energy per access actually is limited compared to the, let's say, the active switching of the logic circuits on the processor. So always the processor is the hottest, and then go to the DRAM and then go to the flash because of the first off, because of the frequency you fetch the data. So the register you get the data very frequently, and then cache, and then DRAM. So DRAM is not that frequent to access data. So you can have the DRAM stacking, but for the processor, it can become very hot. If you cover that with this kind of DRAM stack, then this heat cannot dissipate. Then the temperature of your processor will go up, and then all the performance will degrade at high temperature.
And you not stack the DRAM on the back of the processor die, so then your metal lines and your silicon on the other side of the processor die, so it has enough space to cool off.
Yeah, it may be a better design if you put the DRAM on the other side. Yes. So maybe that's a better design. So, but I don't know why the demonstrations are always like this. There must be some reason.
How will you maintain the same ground plane for both the memories and processor in that case? If stacking it together.
What's your idea?
I don't know, like I'm asking, like how will you maintain the same ground plane for both the processor and the memory?
Ground plane?
So, like if you're bonding out, then all the bonding, like VSS should be bonding to a ground plane. So, if you're stacking the like all the memories below that processor, then we need to also model that ground plane. So how will we do that?
So I don't know, I'm not expert in this TSV technology. So you have something to say?
Professor mentioned the logic active die have more energy consumption and
Yes.
dissipation. Is it only because of the access frequency is higher than DRAM, or the device itself?
So of course the activity factor, or let's say the access frequency, is much higher than the DRAM. But secondly, the logic transistors and those are optimized for high performance, let's say faster switching, right? So you have large on-coverage compared to the DRAM. You engineer DRAM transistor for low power, right? So the no leakage. So the transistor specs are also different. So and also your workloads, or let's say the access pattern, is much higher than in the logic than in the memory.
So in the 3D stacking, are they looking for the same clock speed on logic and memory, or different as you do it now?
What's your question?
So logic and memory run at different clock speed.
Different, yeah,
So
different.
even in the 3D stack case, you would.
Yeah, logic is logic. Yes, logic is logic. So that like a chip level stacking. So each chip is still separate. Yeah, so it's just a better way to do this like packaging. So this is not the monolithic 3D. We're going to discuss later when we talk about the flash. You have learned that through the guest lecture, the 3D NAND flash. That's different. So this one, each layer is an individual chip. Okay, even you take that chip out, it can still work as an individual chip. Okay. So, but for the 3D NAND flash, that's monolithic 3D. You cannot separate the layers. They are like just one structure. You cannot separate. So this is just the individual chips. But the advantage here is to enable the wide I/O because you have so many TSVs. So the I/O width can be much larger than the 2D because 2D. Remember that you see that DIN I brought to the class like last week. So the limited number of pins, you can see that 64, for example. So you can only have the I/O, for example, 64 bits. But for this one, you can have much larger I/O width. You can have more than 64 bits because in this case, those wires only take very small space, like tens of micrometer, compared to, let's say, each pad you need like maybe 50 micrometer, and you only have the edge for the pad. So in this case, you can have the wire in more locations, and each wire actually is like only 10 micrometer scale. So you can have much larger density or more I/O width. So we will see that in the next few slides. So here let's revisit this HBM. So again, this is the schematic of this HBM, like DRAM dies and TSV, and then there will be some logic die, basically controller, and then you have the silicon interposer, and communicate the logic die with the processor, and then everything will sit on the package substrate. So this is the HBM, and it's already in the market. And if you compare the HBM versus the GDDR5, so those are competitors in the market. So the GDDR5 is something like this. You have each individual die. Each die is kind of a high performance die. And then for HBM, you are going to stack multiple DRAM dies vertically. And still, in the center here, you may have your CPU or GPU as your host. So here, let's look at some spec comparison between GDDR5 and the HBM. For example, GDDR5, maybe the bus width, the I/O, is only 32 bits or sometimes 64 bits, but it's narrow I/O, we call it narrow. Because you only have so many pins. But for the HBM, you can have those wires much denser. So you can enable this so-called wide I/O. So each chip can output like 1024 bits at one time. So this means higher bandwidth. However, the clock speed for the I/O clock, this is I/O clock. So in order for the GDDR5 to be high performance, you know, we talk about the DDR, what it means DDR 1, 2, 3, 4, 5, right? So GDDR5, the I/O clock speed is very high, like 1.7 gigahertz. This is already like 5 times, let's say 4 times of the internal clock speed. Because internal clock speed, as I said, typically like 200 megahertz or 300 megahertz at most. Right? We cannot increase the internal clock speed for the DRAM. So what you can do is only to increase the I/O clock speed. So GDDR5 is a good example to increase the I/O clock speed to have high bandwidth. So you have the clock speed for the I/O, and then you have the I/O width, 32 bit. Then you can get the system bandwidth, which is this clock speed times the 32 bits, like 28 gigabytes per second per chip. But for the HBM, since you have wide I/O, you don't need to burst the I/O clock that much. So I/O clock actually is slower, maybe only 500 megahertz. but still you can get a very large system bandwidth simply because you have more bits to send out in parallel in one clock cycle. So the clock is slower, but you have more bits, so still the system bandwidth is very high, even higher than the GDDR5. Question?
Can you explain again what I/O clock speed means?
I/O clock speed is the clock that you burst your data out through to the channel, to the outside. So it's by the I/O peripheral control.
So that after fetching, how fast you can go to I/O?
So we do this so-called prefetch, right? You prefetch multiple bits and burst it out. This I/O clock is the burst clock cycle. Yeah, it's not internal. So you see the benefits of this wide I/O. As a result, the HBM, if you do benchmark versus GDDR5, the bandwidth per watt is like 3 times better than the GDDR5, because GDDR5 actually is very power hungry because the clock speed is so high. So then the power is so high. But the HBM here, the clock speed is lower, so the power actually is lower. But you can get more bandwidth simply because the wide I/O. And also the space, the area in the footprint will scale because you stack multiple chips vertically. So actual physical footprint will be scaled like this. So those are the benefits you can see from the HBM, from the system perspective.
If power is not a concern, can we increase the clock speed for the HBM? Or is
Yeah,
it
you
limited by
can.
some-
You can, but you need to still worry about the heat dissipation, right?
Yeah.
So of course there are some practical limits. So this is the actual application of the HBM. So it was first used in the AMD Fiji chip for this GPU. So this is the first usage of the HBM in the real product. For example, in this AMD GPU, and it used 4 GB HBM placed in those 4 corners, and this is the GPU. But then on the same package, you have the HBM, those 4 corners, and then it has this kind of very wide I/O, 1496 bit wide I/O, and it can enable this 512 gigabit per second. This is bit. You can convert to byte if you wish. This is the memory bandwidth for the GPU. So I think the GPU and the HBM, the business, actually help each other. So that's why they make the success in the market these days. Not only GPU, but also because of this HBM. Otherwise, the GPU does not have enough memory, then it's useless. So later you see that NVIDIA's Tesla, for example, P100, use 16 gigabyte HBM2. So if you look at all of those GPUs available today, they use this kind of HBM. But I noticed that recently I bought one, this Tesla what? We bought one Tesla V, right? Not the Tesla V, Tesla what? RTX. Yes, so you switch back to GDDR6 if you notice that spec. I checked. so it's a GDDR6 Okay, I don't know why. Okay, but still, I think those are still competing with each other. I think Tesla P100 and Tesla V100 use the HBM, and the recent Tesla RTX use the GDDR6. So this is HBM, and this is the trend for the HBM, and basically you can have different applications, and then with the generations and by generation, so the density will go up and the bandwidth will go up. You can look at this slide by yourself. I can skip that. This is just a projection of the trends. And then we can spend a few slides on the embedded DRAM. So this is a separate topic because this eDRAM is not for your main memory. It's not like the high bandwidth memory. So this eDRAM is for the last level cache. If you want to replace the SRAM, for example, with the eDRAM. So the eDRAM is somewhere between the SRAM and the DRAM in terms of the specs. And here, for example, if you look at the cell size and with the speed between SRAM and DRAM, so the gap is about like 20 to 30x, because you know the DRAM 6f squared and the SRAM you know like 160f squared. So, and here SRAM can be very fast, right, like 0.5 nanoseconds. And this way you need like 40 nanoseconds. So there's gap between the DRAM and the SRAM. And the eDRAM is proposed to fill in this gap. So eDRAM is actually the same as DRAM. And it's used as a last level cache. The reason is that it can be larger capacity than the SRAM. Of course, a little bit slower than your L3 cache. You can use it as L4, for example. It's on the same chip as a processor, so that's why it's called embedded with the processor. And the key feature of the eDRAM is that it must be compatible with the logic process. So this is non-standard DRAM. That means it's not for the commodity DRAM. It's compatible with the logic. So that means the logic foundry should do this manufacturing instead of the DRAM vendors like Samsung. So, but this one is so rare these days. So only IBM is producing the eDRAM. But you know, last 2 or 3 years, IBM sold the foundry business to global foundries. Then I guess the eDRAM is no longer being in volume production these days. So this is for the IBM business before. So IBM has the Power series microprocessor, and it all uses the eDRAM, like Power 6, Power 7, Power 8. So the eDRAM's feature is like the cell size is about like 32f squared. So it's not very scaled, because here we care about the performance. So you need to size up the, and for example, the transistor size for the passgate access transistor, and also the spacing in between are also sized up. And then the cell size is about 32f squared. And it uses the trench capacitor. Okay, so this is a key technology that can be CMOS logic compatible. So that means you first do the capacitor fabrication by dig the trench to the substrate, and then you make the transistor here. So this is the trench capacitor we talked about before. Because you make the trench first, then the rest process is just the standard logic process. Because you have done the capacitor first. So this is the IBM's SOI technology with eDRAM. And this is at 45 nanometer technology node. It's used in the Power 7 or Power 8 processors. Since it's no longer in volume production, I think I will quickly skip this part. So this is a summary for the DRAM lecture. And as we see the ever-increasing needs for the larger capacity and higher bandwidth, so the 3D TSV integration is a must for the DRAM system. Even though we cannot really scale the DRAM cell size, but still by the TSV 3D stacking, we can grow the system capacity and bandwidth. So for the really high performance applications, embedded DRAM, as used in IBM, can be proposed as this last level cache. So that's why IBM's power processor can be really high performance. Like the clock frequency for the power is like 5 gigahertz. So it's very high performance. So there's no emerging memory that combines the benefits of DRAM in terms of the speed and the cost and the endurance. We will talk about this in more details when we talk about the emerging memory. There's no emerging memory that can combine all those features together. So that's why the DRAM will not be replaced. So with that being said, if DRAM scaling stops, DRAM will continue to keep its place in the memory hierarchy. So that's the end of this DRAM lecture. Any questions?